A2 only. Okay, in the past, they have asked in A2 paper, what is standard enthalpy of formation? What is the definition of lattice energy? Common, very common, lattice energy. What is the definition of ionization energy? What is the definition of first electron affinity? Okay, it's very, very common. Okay, they will always start with the definition, and it's not limited, okay, to your A2. Okay, do remember, the moment in AS paper, it means they can also ask you anything from your AS. Okay, so it means for AS, for A2, you are preparing for both papers, yeah, AS and A2. Okay, so here, when you have this, okay, I want to write down, let's say, for example, equations. Yeah, so this one, let's say I'm going to use Cl. Okay, so 1 mole of electron is added. So 1 mole of electron is added to gaseous atom. So gaseous atom, Cl, gas, and you are going to get Cl minus gas. So this is going to be the first electron affinity for Cl. Okay, do remember, it's not limited only for like group non-metals or something like that. Okay, even anything, even sodium can receive electron to give you an A minus, but it's not that popular, but still, okay, you can put it, you can force it, and then you can actually get this. Okay, based on the definition, yes, this is the first electron affinity of sodium. Now, this one I have taught you also. Okay, when you have a person, okay, and this person is neutral, and you are trying to bring in electron, which is going to be a negative charge. Okay, negative charge, and you are adding, okay, let's say for example, this is sodium neutral, and you are going to make it into sodium negative, which is going to be a negative, okay, sodium over there. So here, what we can say here is you are trying to form bonds. Okay, you are trying to form bonds between the electron and the neutral atom of sodium. Okay, since you are forming bond, okay, this is going to be endothermic or exothermic, Jonathan?
Forming bonds is...
Always remember, forming bond, you want to get married. You used to be single. You always go to party. You are having a lot of energy, and you want to get married. You have all this energy, but you cannot go to party anymore. What had happened to your energy? It's all go out in terms of frustration. So you are going to be vibrating, release all the energy out. Okay, so that is going to be exothermic. You are releasing the energy. Okay, so if you have that problem, always remember in that kind of a manner. Yeah, forming bond is exothermic. Okay, breaking bond is going to be endothermic. So this is going to be exothermic. But now, okay, for ionization energy, okay, you can see that, okay, I didn't write down over there. Ionization energy is always going to be removing the electron. You are trying to break the bond. Okay, if you break the bond, ionization energy is always going to be endothermic. So you see, I have taught you, okay, one atomization is going to be always endothermic, lattice energy is always exothermic, and now you have ionization energy, which is going to be always endothermic. There is no but, okay, it's always, okay, it's always going to be endothermic. But here for activation, sorry, why activation again? So for the electron affinity, okay, for the electron affinity, there is no like a conclusion. It's going to be always, okay. There is but, okay. So it means now, okay, if you are negatively charged, when I bring in electron, okay, which is also going to be negative, what will happen? The same charges, they will repel. Okay, but I don't care. Okay, you don't like the let's say electron. Okay, they don't like the sodium or sodium ion or something, the negative ion. Okay, something like Indian traditional marriage. Okay, you don't care whether these two people like each other or not. Okay, you just make them to like each other. Arranged marriage. Okay, you make them to actually go together. Okay, even though they repel. Okay, make them go together. So it takes a lot of effort from the parents from both sides. Okay, then force them. Okay, get married. Okay, so you are going to use energy, okay? Because they are repelling, it requires energy, okay? You need to have energy, okay, from the environment to form that bond, okay? To form that bond, not simply just form, okay? But now you need to really push them together and then to overcome the forces of repulsion. So that will make, okay, your earlier, the first electron affinity was exothermic, but your second electron affinity is going to be endothermic because of the forces that is repelling. Okay, you need to do it differently. The same thing will apply for your third electron affinity. It's also going to be positive. But don't ask me about the fourth and so on. I'm not sure. Okay, but up to your book, they mention about the third. And then first is always negative, second and third is normally not normally, it's always positive. Okay, it's always positive. Okay, but the other details you can find it later. Okay, but we will focus in the textbook only. Yeah. So here first EA is negative, followed by the rest is going to be, not to say the rest, second and third is going to be positive. Okay, the reason is given to overcome the forces of repulsion. Okay, now if I put this, okay, like for example, now, okay, I have the first electron affinity, second electron affinity, third electron affinity. Okay, now according to your syllabus now, okay, they want you to talk about the trend. Okay, what is the trend that they want you to talk about? Okay, the trend of electron affinity. Previously, in your previous syllabus, trend of electron affinity, even in your old textbook, okay, I will refer your textbook as old now. Yeah, so the old textbook, okay, the blue textbook, okay, they will not write down the trend of electron affinity because generally when we look into the electron affinity, there is no clear trend. Okay, there is no clear trend. So we never bothered about it. But I think the new syllabus, they want you to focus a little bit on that because they are being very specific. How specific they want to focus? They only want to focus somewhere here. Okay, which is going to be your group 17 and group 16 and 17. Okay, 16 and 17. Maybe if you want to include 15 also, okay, 15, 16, 17. But in your syllabus, okay, they specified it very clearly. They mentioned about trend in group 16 and 17. Okay, what trend? One, they want to go across, okay, basically to go across, or you can just say when you go across non-metals, okay, when you talk about non-metals, means group 15, 16, 17, okay, so you can also include 15, yeah. But another trend that they want you to talk about is the trend you go down, okay, not group 15 and the others, okay, not even group 1 and so on. They want you to talk about the trend for group 16 and 17 only. Okay, 16 and 17 only. So when you look at the trend, okay, the first thing, okay, you need to know there is no clear trend. Okay, that is the first thing that you need to take note. There's no clear trend. Okay, but when you look into certain portions, okay, certain portions, okay, maybe between here to here, yes, you can actually derive some sort of conclusion. Okay, some sort of conclusion about the trend. Sorry, I got disconnected for a while. Okay, when you go across, okay, when you go across from left to right, okay, maybe you can come up with some sort of a trend. When you go down, okay, when you go down group 16 and 17, if you ignore, okay, I will just put it over here. If you ignore the first, okay, something happened with the screen sharing. I will share it again. Hold on here. Okay, I got disconnected from my iPad.
Sir?
Yeah.
This is the trend for what?
Electron affinity, Nevan.
First electron affinity only or what?
Okay, for your syllabus, they will focus on your first electron affinity because since you know the second electron affinity and the third electron affinity, they are positive. Okay, in your textbook, they always mention whether it's more negative or less negative. It means they are referring it to your first electron affinity. Even there is no specific sentence saying that they are referring to electron affinity, the first one, it is understood if they are talking about negative. Yeah, if it is talking about negative, they are referring to your first electron affinity. Yeah. So hold on. Yeah, my iPad is disconnected currently. Okay, while it is being connected, okay, so I will just also keep on going. Yeah. So basically, okay, when you look into this trend, yeah, the trend is because they say there is no clear trend. Yeah, please ignore the first period. Okay, please ignore the first period, or just ignore, like for example, if you have group 17, right? Okay, group 17, they always start with what? FCCBI, right? So fluorine, chlorine, bromine, and iodine, and so on, right? So this trend doesn't include fluorine. Okay, the first one. Okay, it doesn't. Okay, but apart from the first one, the rest of them, they will follow a proper trend. Okay, that is going to be according to the definition. Yeah, they will follow the trend. So we will follow that trend. Okay, hold on, guys. Okay, we will follow that trend. Okay, hold on, I'm joining. So it means we will follow from the second period downwards. Okay, going down. Give me 2 minutes. Okay. So I was mentioning about this just now. Okay, there is no ignore the first period. Okay, ignore the first period of group 15, 16, and 17. But we will look at the trend outside of the period 1. Yeah, outside of the period 1. So in order to understand this better, okay, we have to look at similar to your ionization energy. Okay. So since we are just looking into that portion of group 17 and group 16, okay, so I will just put focus over here. So if let's say if group 16, group 17, I know that this one, if it is bigger, this is going to be smaller, okay, within the same period. Okay. So we know that, okay, what happens here, the reason why it is smaller, because there is a same, okay, constant shielding, okay, same number of shells and so on. Okay, so there is more proton. Okay, so if I just put it over here, more proton, it means just assume that the attraction, it means the nucleus is going to be, even though they are neutral, I'm just going to put this as positive. Okay, this the one that is going to be smaller, they are going to have a better positive nuclear charge compared to this one. Okay, compared to this. So now when I bring in electron, okay, when I want to try to add electron in, the electron, okay, will be bonded, okay, it will be better bonded when they are having opposite charges, of course, okay. And if you have more positive, of course, the electron will like the one that is more positive, yeah. So if they are forming, if you have here, the bond that is being formed over here, if you compare with the bond that is being formed over here, there will be a better bonding that will happen between the group 17, okay, with the electron compared to group 16 with that electron. Okay, since there is a better bonding that is taking place, it means that this is going to be bond formation. Okay, so it's a bond formation, so it's going to be exothermic. So if I put it in terms of numbers here, in terms of numbers, let's say I give you a number. Okay, this is -90, for example. Okay, and this one, if I ask to predict, maybe -40. Okay, -90, -40. So what conclusion that you can come about over here? The conclusion is, as you go across, okay, it is going to be the first electron affinity is going to become more negative. I hope you understand this. Okay, the first one. Okay, they are going to be more negative as they go across. Why? Because they can form bonds better. So now let's look into this going down the group. Okay, we know the first period. So let's go down the group. Let's say I'm going to use this same example, but now going down the group is getting bigger and bigger. Okay, so getting bigger and bigger. We know, okay, we know that, okay, the same thing will take place over here, even though the proton number is increasing. Okay, the shielding effect and the distance are also increasing. So the shielding effect and the increase in distance will outweigh the increase in the number of protons. Okay, so if I just ignore the positive just now, yeah, so I will erase this one first. Okay, if I want to just put which one is going to be more positive, yeah, which one is more positive, okay, you see that, okay, the one that has, okay, supposed to be the positive charges, right, they are going to be decreased as they go down. Why? Because it's shielded and there is going to be distance is more. Okay, so let's say this is going to be more positive if you compare to this. Okay, the one on top is more positive. Okay, the one on top is more positive. So now if I want to introduce my electron, okay, if I'm introducing my electron here and here, okay, where the electron will be attracted easily. Okay, if you look over here and here, you can clearly see that electrons are going to be attracted to the one that is more positive. Okay, so electron will be formed, the bond will be better formed here, okay, the one at the top, okay, compared to the one that is at the bottom. And this one, since bond formation is going to be exothermic, okay, so this is going to be, we can say this is more negative, okay, compared to this. But let's say we look at into numbers, for example, okay. So if let's say I'm giving you a number, maybe -100 over here, okay. If they say the top is more negative than the bottom, okay, so you just say maybe at the bottom is -40. Okay, -40. So if you look at the trend, you want to come up with a conclusion, okay, when going down, you can say the EA as you go down, okay, for both group 16, 17, maybe 15, okay, as you go down, they are going to become less negative. Okay, so what is important over here? Okay, the most important stuff is not only memorizing that they are going to be more negative, not only memorizing that they are going to become less negative, you need to understand why. Okay, you need to understand why based on my explanation over here. Okay, how can they ask questions related to this? Okay, I'll just give you some examples. Okay, let's say this is going to be group 17 and you have X, Y, and Z. And they are going to be arranged. Let's say, for example, this belongs to period number 4, period number 5, period number 6, for example. And they ask you to compare the electron affinity of X, Y, and Z. How do you compare? Okay, so very simple. Okay, you can compare, okay, based on, okay, you know that this is smaller, this is bigger, this is way bigger. Okay, and then you know that the shielding effect and the distance is going to play a big role over here. So it means this is going to be more positive, less positive. So if I want to bring in electrons over here from somewhere, they are going to be attracted to X more compared to the electron attracted to Z. So what happens here is going to be, this is going to give you a bond formation will be there. So more exothermic, okay, more negative, Okay, I'll erase this. I'll just say more negative, and this is going to be less negative because of bond formation. Yeah. And then if they ask you to compare group 16 and 17, for example, let's say within the same period 5. Okay, period 5, you have Y and then you have A. Okay, and this one maybe A is okay. A, I just put it over here. A is going to be group 16. This is group 17, and I want you to compare between A and Y. How do we compare? Okay, quite simple also again. Okay, within the same period. Okay, and you want to compare them. Okay, got disconnected for a while, I think. Okay, now within the same period, okay, you want to compare. Okay, we know that this is going to be bigger, this is smaller. Okay, bigger and smaller. And I know it is getting smaller because more number of protons, so it means that they are more positive compared to here. When I bring in electron from somewhere, okay, the electron will be better bonded here, okay, compared to the here. So it means that Y is going to be more negative. Okay, the EA, okay, electron affinity is more negative compared to. Okay, I hope you understand how they can ask you this question. Okay, will they compare this, that, and so on? We don't know because this is the first time that they have introduced this syllabus, and you are the first one, okay, the first batch who will sit for that syllabus. So we will know later, yeah. So this is very new. I've never seen any questions yet on this, okay, but I don't think so it's that difficult. Okay, still okay, manageable, yeah. Now, since we have learned all this, okay, I will just come back to this Born-Haber cycle. Using all this, okay, they are going to actually look into Born-Haber cycle. Born-Haber cycle is an extension of your Hess's law. Okay, if you sometimes they'll ask you to define Hess's law. Okay, the overall enthalpy change or the total enthalpy change is independent, okay, of the route taken. Okay, so you can actually go and look for the definition from your textbook. Okay, so Born-Haber cycle is also the same. If I come back to here again, the beginning part, I told you earlier there are total 3 things. Okay, there are 2 more additional stuff I asked you, and one of the additional stuff that we mentioned is endothermic and exothermic. But there is another one more point that you can add, okay, for this enthalpy of atomization and lattice energy. Now, lattice energy cannot be determined, okay, cannot be determined experimentally. Okay, cannot be determined experimentally. It must be calculated. Okay, must be calculated. So how do we calculate? We will use Born-Haber cycle. That's the reason why the Born-Haber cycle exists as a at the first place. Okay, we can get all the information: enthalpy of atomization, enthalpy of ionization energy, and electron affinity. You can get all this data. Okay, not through our experiment in our lab. Okay, but under control situation, you can get all these values. Okay, but okay, you need to calculate, okay, manually, okay, for the lattice energy. Very, very important. That's why it will go at point number 3. Okay, and this is the reason why we have Born-Haber cycle at the first place. Very important. Okay, because we will use Born-Haber cycle to calculate lattice energy. And how it is going to be calculated, that is the reason why we learn the definitions of all these energies at the first place, because we need to know why, when to use them. Okay, I'll give you one example over here: enthalpy of formation. Okay, enthalpy of formation, if you by definition, okay, enthalpy of formation is going to be enthalpy change when 1 mole of compound, okay, 1 mole of compound is being formed from its element, not gases or something, from its element under standard condition. So if I want to write down the enthalpy of formation of, let's say, sodium chloride, okay, you are forming sodium chloride under standard condition. They are going to be under solid. And you are forming it from what? Element is going to be solid. The element for chlorine is Cl2, so half, and then they are gas. This is the enthalpy of formation, the equation for formation of sodium chloride. Okay. Now, this formation can be either negative or positive. Please remember, formation is not fixed. Okay, not just because they are forming and then you say it's forming a bond. No, okay, they are not fixed. They can be either positive, they can be negative also. Okay, but let's say I give you a clue, because if you want to draw Born-Haber cycle, you must have some clue. Okay, so especially for this, I think this one I give you a clue. This is going to be negative. Okay, I give you a clue. How do we know? We won't know. Okay, but I'm just giving you a clue. Okay, it's negative. So I will start using this. Okay, how do I draw the Born-Haber cycle? You start, okay, from NaCl. You start NaCl solid. You start from there. And how do you form NaCl? You form NaCl from Na and Cl2, and it's exothermic. So you put like something like your energy profile diagram. It's an exothermic. So the reactant is at the top. And you are forming it from sodium solid and Cl2, which is going to be half Cl2 and gas, like what we had just now. Okay. So this is going to be enthalpy of formation. Okay, enthalpy of formation. And I'll just put it as number 1. Okay, number 1 is enthalpy of formation of sodium chloride. Do remember, it can also go up. Okay, it can also go up depending on the situation, but now I'm using it as going down because they have mentioned. Now, if you want to continue with this to find the lattice energy, okay, there are certain steps that you need to do. Okay, so first you need to change sodium solid into sodium gas. Okay, this one untouched. Okay, so this one, sodium solid to change sodium gas. This is enthalpy of what, Kiera? Yeah.
Atomization.
Yes. So this is going to be enthalpy of atomization of Na. Okay, so I'm going to put it as 2. And it is endothermic. That's why it's going up. Okay, it is endothermic. And then leave it as it is. I'm going to change this Cl2 into atom also. Okay, Cl gas. Okay, and I'm going to have Na gas. Okay, so how come from Cl2 become Cl only? So because of the half, yeah, because of the half. Okay, so it's going to actually change into Cl, one single atom of Cl. Yeah, one single atom of Cl. So this is going to be enthalpy of atomization of Cl. I'm going to give it as number 3. Why? Because this is also going to be endothermic. Okay, you're breaking bonds. Next is by starting to make them into ion. Okay, let's start with Na. First, ionization energy. You have Na plus, okay, gas. Na gas to become Na plus gas. You will get electron. You are removing one electron. And then the Cl will stay. I'm not doing anything with the Cl. So this is the first ionization energy of Na. And I'm going to give it number 4. And it is positive. First ionization energy is positive. The next, do remember our aim is to form NaCl. Okay, our aim is to form NaCl. So I need to have Cl minus. How do I get Cl minus? By joining these two together. So how do we join this Cl and E together? So this is going to be your electron affinity. Okay, they are in gaseous form and you have electron. And this electron affinity, are they going to go up or go down, Ella?
Go down.
Very important, because your first electron affinity is going to be negative. Okay, see, it will go down. Okay, so I am going to draw maybe to my right another line. So maybe I'll extend this and I so that it is going down. Okay, it is going down, and this is going to be, I'm going to have Na plus gas, and then the electron and Cl join together, so you will have Cl minus gas. And this is going to be represented, okay, with my electron affinity of Cl. Okay, I'm going to give it as number 5. Okay, number 5. The rest, okay, what is next? You extend this from here to here. Na plus gas, Cl minus gas to give you NaCl solid. What is that, Jonathan? Enthalpy of what?
Formation.
No. You see, yeah, enthalpy of formation is going to be from its elements. Okay. This is going to be ion and gaseous ions.
Is it lattice energy, sir?
Yes. Okay. This is lattice energy. Okay. Gaseous ion. This is the one that we are looking for actually. Yeah. This is lattice energy. So I'm just putting it as H lattice. Okay. So I'm just going to put it as number 6. Okay.
So
Yeah.
for the left side, for the enthalpy of atomization, does it matter if you put the chlorine or the sodium first?
Doesn't matter because they are still going to go up.
Okay.
Yeah, doesn't matter. Okay, so they are still going to go up. Doesn't matter what position that you put. Okay, but if you follow through like this, as long that they can join together to give you like something like this, this is called Born-Haber cycle. Okay, this is called Born-Haber cycle. And how do we use this? Okay, depending on what you want to find out. Okay, because we use the Hess's law, the previous method that I taught you, clockwise equals to anti-clockwise, you can apply over here. If I want to use the clockwise equals to anti-clockwise, okay, let's say I'm going to draw a circle over here. Okay, so I can change, okay, the arrows that we have over there slightly. You see, clockwise, 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 still clockwise. Okay, this is going to be anti-clockwise. Okay, so if I put this, okay, so this one maybe I'll just ask Jackson only. Can he understand? Jackson, are you there? Can you understand this part, Jackson? Wait, is Jackson here?
He's not in our class, I think.
Oh, Jackson went to JC2. Okay, sorry guys. Yeah, so I have a new guy in JC2. Okay, not your class. Okay, it's okay. So anyway, so all of you should understand. Yeah, because none of you are new here. Yeah, so only Jackson, okay, is came from Miss Chandira's class to my class. Yeah, so I want to also teach him my method, but all of you should be familiar with my method over here, which is going to be the clockwise equals to anti-clockwise. Yeah, so if you look over here, okay, so this is going to be, if I want to write down according to Hess's law, it will be clockwise, so it's going to be number 2. Okay, number 2 plus number 3 plus number 4 plus number 5, which is the negative value. Yeah, so I'm just going to take the magnitude only. Yeah, so number 5 plus number 6 is going to be the same as number 1. So most of the time we want what is 6. So you can use your mathematical formula, can balance, bring everything to the right, and then find out number 6. Okay, and solve it. Okay, this is Born-Haber cycle. Yeah, Born-Haber cycle. Of course, I've drawn for sodium chloride. Okay,